general behavior of the series? Well, our series, of course, is going to begin with P naught. We don't know yet what P naught is and what would determine it, but we might guess it's going to be related to an overall normalization constant. Now let's see what else we can say. If I now apply this equation with the value n equals 0, it tells me P1 in terms of P0. In fact, it tells me that P1 will equal, and since I'm using n equals 0, n is 0 in here, so I have alpha times L plus 1 in the numerator minus 1, then divided by n is 0, so I just have these terms, L plus 1, because again n is 0, times P0. So I can get the next term in the sequence very nicely. If I want to get P2, I can apply the same formula again, but now I need to use n equals 1, which will then give me P2 in terms of P1, and then these factors, but now n equals 1, so what I have is alpha on top times now L plus 2, because n equals 1, minus 1, divided by, on the bottom again, n equals 1, so I get twice L plus 1, and then n is 1, so plus a half. So 1 plus a half is actually 3 halves. Let me write that down a little more carefully, times P1. But, of course, I know P1 in terms of P0, right? So I can write this a little bit more complicated, I guess, but it tells me how the sequence is behaving. I'll have an alpha, L plus 2 minus 1, divided by these factors, L plus 3 halves. And then this ratio is multiplying P1, but P1 is this factor times P0. So that's times an alpha L plus 1 minus 1 on the numerator, and in the denominator I have an L plus 1, and all of that is multiplying P0. So now I think we get a general feel for what the general term in the series is going to look like. Pn, the nth term in this sequence, you will notice, in all these cases, as I keep applying my recursion relation, every single term ends up being simply proportional to P0. So I could factor out that P0, and then the remaining pieces that I have are like a ratio like this or a factor like this. They are very complicated factors. They depend on n, which p I'm trying to generate, some crazy function that depends on n, and the function itself just depends upon our parameters, alpha, which is this key parameter related to the energy, and the angular momentum label L. Now we can imagine that that is the general appearance of our series. So then if I want to understand the function p of r, that is going to be, of course, my power series, sum on n, pn r to the n. Well, I can substitute in this form, and I can always factor out the p0. So it's going to be p0 times sum on n, n goes from 0 to infinity, of these crazy functions of alpha and L, times then r to the n. And that's my general behavior of my function p, where then we see p0 is nothing other than a normalization constant we can use later, determined by the norm of our wave function. Wonderful. Now, so we've got now our full solution. The real question, the key issue at hand, though, is how our function satisfies our boundary conditions. That's always what leads to the allowed values of the energies. We've already ensured by writing down this factor of r to the L plus 1 that we are obeying the appropriate boundary condition at 0. Where we haven't imposed anything yet, if you think about our solution, is out here towards infinity, right? We have to make sure that our solution out here is an exponentially decaying solution and satisfies the boundary conditions. So we very much need to understand how our p behaves as r heads off towards infinity. So we need to check then our boundary conditions. And when r goes to 0, we've already satisfied that. But we have to investigate what happens as r goes to infinity. Now, looking at the form of our infinite series, as r heads towards infinity, I hope you can see that the terms that are by far the most important are the very large powers of r, right? Those will be the most important terms. So what's really important in this series is how things behave as a function of n. That behavior will be dominated by large n goes to infinity terms. So it's those that we really need to understand. Now, as n heads towards infinity, our recursion relation is then going to become quite a bit simpler. This is what it looks like for ordinary n. But as n becomes very, very large, what we will find then is that Pn plus 1 is going to equal some ratio times Pn. And this ratio is going to very nearly approach the following. As n becomes exceedingly large, the numerator is very well approximated by just the largest term, which is this alpha n term. So I will have an alpha n on top. In the denominator, these terms will be dominated by the quadratic term in n. That's the highest power of n. So that will go like n squared over 2. So to a very good approximation for those terms that dominate the behavior of this function, we find that our recursion relation reduces to a factor of 2 alpha on top divided by n multiplying Pn. Next, if we want to think about then what is happening to these terms, notice the basic structure that we see. This tells us that, again, to a pretty good approximation for very large values of n, P is going to look something like the following. Every time I move up 1 in my series, I pick up an extra factor of 2 to the alpha, and I get divided by n. Now, I don't know what's happened for the earlier terms in my series, right? This ratio is not that well approximated there. But beyond a certain point, this is the factor that I'm seeing. So I can say conclusively that the very large values of n, right, the terms there are going to be like some proportionality constant, which I will call b, right, times 2 alpha to the power n, because I need an extra 2 alpha every time I move up in the sequence. And in the denominator, notice I'm dividing by n times n plus 1 times n plus 2, etc., which is exactly reproducing this series, of course, the product for n factorial. So this then tells us as r heads towards infinity, right, I therefore know that P of r, which is controlled by precisely these terms, will have a behavior that goes like sum on n, Pn times r to the n, but Pn is b 2 alpha to the n over n factorial times r to the n, where, recall, this is just my Pn to a very good approximation. When my sum looks like this, of course, I can pull out the factor of b, and then what remains for my P of r is a series where I can combine my factor of r, it's 2 alpha r to the n, over n factorial. And I hope you recognize this power series. This is a very famous power series. It is in fact the power series for the exponential function, where the quantity that's raised to the power n is the exponent. So this is e to the 2 alpha r. So we see actually that our function P of r is going to be blowing up as r heads towards infinity. But P of r is not actually our main concern. Our main concern is the wave function itself, rho of r. But rho of r is r to the L plus 1 times an e to the minus alpha r, that's this decaying exponential, times now this prefactor b, which is multiplying e to the 2 alpha r. So the final behavior is some r to the L plus 1 times some b times e to the plus alpha r. So unfortunately, this actually diverges. So this is not normalizable. It's not normable. Now, this isn't completely random, actually, or unexpected, so we shouldn't be too discouraged that we haven't found any solutions yet. This form, b times e to the alpha r, is not really a surprise. Think about it. The behavior we were expecting out here was precisely some arbitrary linear combination of a decaying exponential and some exponential that's growing, something exactly like e to the alpha r. So this is really what we expected. And it's not a surprise because in general, as you know, for arbitrary values of the energy, in other words, for arbitrary values of alpha, we always expect we are getting these exponential divergences. It's only the very special, the discrete values of alpha or e that allow us to actually eliminate exponential growth and to find something that actually is normalizable. So we need to find some kind of a special condition, a special loophole that gets us out of this inevitable exponential behavior.